Hello, everybody. We are back, and we are going to start Chapter 7 now. And like I mentioned at the end of the last video, Chapter 7 is where stuff really starts getting real in a lot of ways, because this is the first of many chapters where we will do a lot of reaction chemistry. Obviously, there's many aspects to the class and many different concepts that we'll learn, but reaction chemistry is going to be hugely important from here to the end of Organic 2. All right, so Chapter 7 is all about a group of compounds called alkyl halides. So you're learning about a new group. Okay, alkyl halides are just simply hydrocarbon structures that have halogens attached to them, right? So we can represent them in a general way by this. The R refers to a carbon chain, which I think I've mentioned before. Hopefully I have. Crud. There we go. But I'll remind you of it. X always is the generic terminology for a halogen. So, you see X, that means, it can stand for fluorine, chlorine, bromine, or iodine. Excuse me. All right. Now, the first thing that we need to do is we need to be able to recognize what type of alkyl halide that we have. And there's several different types, actually, some of which will be more important than others in this chapter. All right. First type is a primary alkyl halide. All right. And it's very simple to recognize a primary alkyl halide. A primary alkyl halide is one where the halogen is attached to a primary carbon, right? So, something like this, right? This guy is a primary carbon, so Br is attached to it, primary alkyl halide. Very, very simple. Something like that, also a primary alkyl halide. And you're going to see a pattern here. What do you think a secondary alkyl halide is? It's exactly what you would think, right? It's going to be an alkyl halide where you have a halogen directly attached to a secondary carbon. So something like that. Something like that. Examples of secondary. And tertiary, you're starting to see a pattern here. Tertiary alkyl halides are going to have the halogens directly attached to tertiary carbons. Something like that. Something like that. All right? It's a pretty simple matter, but it's going to be extremely important because we're going to be learning about a couple of different mechanisms in this chapter, and also a couple of more in Chapter 8. And depending on what type of alkyl halide you have will determine what type of mechanism you go through. And that, therefore, determines the products, right? So it's a very simple concept, but it's one that's very important to get early on. These are going to be the three types that you're really going to be concerned with the next couple of chapters. Just to give you a little bit of a preview, there's a couple of other types of alkyl halides that we will run into eventually, and that will be also very important to recognize. Okay? And there's specifically going to be examples wherever you have halogens that are directly attached to carbons that are adjacent to double bonds. That's kind of wordy, I know. But let me define this. The spot directly adjacent to a double bond, like this is referred to as an allylic carbon. Okay? And therefore, if you have a halogen attached to it, that is an allylic alkyl halide. Okay? And, they have their own sort of set of stabilities and reactions that can happen, but they still fall under the alkyl halide umbrella. We can even sort of make a subdivision of allylic alkyl halides, specifically when there's a benzene ring, or any type of aromatic ring, I guess. Actually, no, it's specifically a benzene ring. All right. If we look at this carbon right here, this carbon, again, is directly adjacent to a double bond, but specifically, it's adjacent to a double bond in a benzene ring. That is referred to as a benzylic carbon. And overall, this would be referred to as a, if we had an X attached there, that would be a benzylic alkyl halide. All right. So all 5 of these that I just went over fall under the alkyl halide umbrella. We're not going to really worry about allyl, and we're not going to worry about benzyl right now. All right. All right. And just to also give you a heads up, there's a couple of other species that look very similar to alkyl halides, but they're not. They're not classified as alkyl halides. They do other things, so don't get mixed up with them. So I guess I can just say not alkyl halides. All right. One case you might see a halogen directly attached to a carbon that's in a double bond, something like that. This is referred to as a vinyl halide. They undergo very different types of reactions than alkyl halides do. All right. You can also have a halogen directly attached to a benzene ring. That's called an aryl halide. All right, and those do not fall under the umbrella of alkyl halides, so be careful not to get them mixed up. One pro tip here. If it is an alkyl halide, the carbon that has the halogen will be sp3 hybridized. And you'll notice in this case, each of these carbons are not sp3 hybridized, they're sp2. Okay? So don't let those trip you up. All right. So in a second, we're going to get into the real teeth of this chapter, which is, reactions. But first, we have anytime we introduce a new family of compounds, we always like to learn how to name them. So let's talk a brief bit about nomenclature. Nomenclature of alkyl halides is very simple, and you can use mostly the existing rules that you've learned with alkanes and just sort of add, a little bit to it. All right. There's a couple of different systems that you can use. All right. As always, the most important one is IUPAC, the systematic way. So that's the one I'm going to go over first. All right. All right. So first thing you do, just like with alkanes, is find your parent chain or ring, as it may be. Okay. And you're going to name this parent part just like you would normally. Name it as an alkane. So, propane, butane, hexane, cyclohexane, cyclopentane, etc. Okay? All right, the only difference is that alkyl halides are going to specifically have halogens as substituents. All right? To name a halogen as a substituent, here's what you do. All right, I'm just going to use the Cl, chlorine, as an example. What you do is you take the name of the halogen, so like chlorine. To name it as a substituent, what you do is you take it, you drop the I and E, and add an O. So chlorine becomes chloro. Fluorine would be fluoro, bromine would be bromo, iodine would be iodo. Okay? And then lastly, just very simply, apply all other rules of nomenclature that you've learned so far. Okay? When you're counting, trying to number the chain, you treat it the exact same way. Just to pretend that halogen is an alkyl group, right? You still follow the same rules. If there's a tie, you still use the alphabet to figure out which end is which. All right, so it's very, very simple. And I'll show you a couple of examples here. So, oops. Crud. Got like a half-second lag in between my stylus inputs, so it kind of trips me up sometimes. All right, so let's say we had this, right? Well, first we identify the parent chain. I think that's going to be 5 carbons, and we can do that straight across, pretty easy. Calling, she's going to have to wait. All right, so that's how much I care about you. I'm probably going to get in trouble with the wife later on for ignoring her call, but that's how much I care about you. Okay, so we have pentane. All right, numbering, definitely want a number from the left-hand side because that gives the substituents the lowest numbers. All right, so we have a chloro at 3 and a methyl group at 2, right? Chloro comes before methyl alphabetically, so we're going to write that one first. 3 chloro, 2, running out of room, methyl. I'll have to sort of write it up top, but you get the idea. Okay? It's like something like this, right? All right, so our parent there is cyclohexane. We've got an ethyl group right here, a Br right here. We know these carbons are going to be 1 and 2 in some order. Since the Br comes before the ethyl, E for ethyl in alphabetically, this one's number 1, this one's number 2. So we have 1 bromo, 2 ethyl, cyclohexane. Okay? All right, one more. Well, let's make this one bigger. Well, let's put 2 halogens on there. Spice it up a little bit. Okay? All right, so if you look through this, I think you'll find that the longest carbon chain is 7, if I did this correctly, which I'm pretty sure I did. So 7 carbon chain, that's going to be heptane. All right. Excuse me, we have 3 substituents on it. If we go from the right side, we get the lowest possible number. So we have an iodine at 2, we have an iodine at 3, and we have an isopropyl group at number 4. Okay? All right, so I for iso comes before, let's see, let me think about it. Iso and iodo. Ooh, those are very close. Actually, iodo comes first. Remember, we don't use D for diiodo, we use I for iodo. All right, so we're going to have 2, 3, diiodo. Kind of funny to say, but that's how you do it. 4 isopropyl heptane. Viola. Very good. All right. So that's the IUPAC system. There is one other method that's used. We do actually have a common name system. Occasionally common names do have a system. And this works very well for very, very simple alkyl halides. If you get more complex, sort of like that last one we just did, this isn't going to work. All right, but it does work for some for some very simple ones, and you will see these used quite a bit. All right, so for the common name system, here's what you do. All right, so you look at your structure and you name the carbon chain as an alkyl group. All right. Then you take the halogen and you name it as a halide. All right. What does that mean? Well, again, I'll just use an example here. I'll use chlorine again. All right. When you're naming this as a halide, what you do is you take, whoops. You take the original name, chlorine, and basically what you do is you change the N to a D. So instead of chlorine, it's chloride. And then that's basically it. Then you just combine them. The alkyl group goes first, and then the halide is last. So if you had something like this, for example, right? This group over here, this is 2 carbons, so that would be an ethyl group. F is fluoride, that would be ethyl fluoride. Okay? You could take something like this. Oh, that's a terrible pentagon. I'm so ashamed of myself. Right? If you wanted to name this with the common name system, well, you have cyclopentane, which is a cyclopentyl group. And we could call this cyclopentyl chloride. I should make it known, however, you can still name each one of these examples by the IUPAC name. The IUPAC name for the top one, by the way, would be chlorocyclopentane. The IUPAC for the bottom one would be fluoroethane, right? But you can use the common name system for simple ones like these. All right. That is about it for nomenclature. Like I said, very, very simple. If you have any questions, let me know. All right. So let's get to the big part of this chapter, and let's start talking about the reactions of alkyl halides. All right. Well, first let's ask ourselves, why are alkyl halides reactive? They are very reactive species. They can be used, in lots of different types of reactions, and this is because specifically of that carbon to halogen bond. Right? It's a very, very polar bond, and this makes sense, right? Because halogens are highly electronegative, right? So electron density is being pulled this way, and so you have a definite partial negative on the halogen, and most importantly, a pretty strong partial positive on that carbon. And what this does is this makes this carbon a really good target for a nucleophile. And that's what I'm using NU to stand for, is nucleophile. Right? So, the reactions that we're going to go over in this chapter are called nucleophilic substitutions. And really the name is very descriptive here, right? They're going to be substitutions. Something is going to come in and replace the halide in these structures. And it does so because you have some sort of nucleophile that's attracted to your carbon. All right? So if we wanted to sort of write a general reaction for this, we could just simply say something like this. Yeah, and of course this is more nuanced. There's lots of stuff to this, but in general, this kind of tells a large part of the tale. All right, so let's take a look and see what requirements we have to have in order to have nucleophilic substitutions. All right, there's some pieces, there's some ingredients. As in any great recipe, there are ingredients. All right, so let's take a look. Components of nucleophilic substitution. All right. Your book lists 3 in this list. I'm actually going to list 4 of them because there's another one that it does talk about, but it doesn't explicitly kind of mention as being important. I think it's important enough for the list. So let's take a look at them. All right. The first thing that you have to have is you have to have an sp3 hybridized carbon that's attached to something that's going to create a really good dipole. All right. For our context here, we're looking at alkyl halides, so we're going to say something like this. All right. So basically, we need an alkyl halide. All right. Now, part of that compound must be something called a leaving group. Leaving group is exactly what it sounds like. It's a group that, well, leaves. Okay? And you saw this in crap. Sorry, my U was poorly made, so it was bothering me. All right, so you saw in that, just that general reaction that the halogen acts as a leaving group. Halogen takes its electrons and it leaves. It goes away. All right? Different types of leaving group can be different qualities. Some things work as really good leaving groups, some things don't. So we'll talk about, what determines that. We got to have a nucleophile of some sort. Now, the example I just showed you in the general reaction was negative. It was like this. It doesn't have to be negative necessarily. It just has to have at least one available set of unshared electrons to donate. A lot of times it isn't it does form a negative charge, but you can have neutral nucleophiles as well. They don't necessarily have the same nucleophilic power, but they certainly can act as nucleophiles. All right, we'll talk more about that once we get to nucleophiles. And then here's the component that they didn't explicitly list, but I think is important. And that's the solvent for the reaction. Generally speaking, whenever you do these, you're going to have to add some sort of solvent. All right? And we're going to see that certain mechanisms, certain substitution types, tend to run better in certain solvents, for one thing. And also, the type of solvent that you use can actually change the nucleophilic power, or can affect the nucleophilic power of your nucleophile, which is pretty interesting. All right, so we're going to take a look at these different components in greater detail. Come on. All right. The first thing is the alkyl halide itself, right? And this is where being able to identify whether it's primary, secondary, or tertiary is important. So, first thing you need to be able to do is identify primary, secondary, or tertiary as the type of alkyl halide that you have. All right? That's really all that you need to know about alkyl halides at the moment. All right, let's talk about the leaving group. Like I said, some things make good leaving groups, some things make poor leaving groups. All right? And luckily, we have a periodic trend that we can use to help predict this. All right? Generally speaking, the weaker the base, the better the leaving group. And the periodic trend that you can see is like this. If we're looking at a periodic trend and we're measuring basicity, that's basically how strong or how powerful the base is, right? You get more basic as you go from right to left on the periodic table, and as you go from bottom to top. Right? So the most basic, species tend to be in the upper left corner. All right? Well, we saw that to be a good leaving group, you kind of have to follow the opposite of that. So, if we want to, map out leaving group ability, it's going to be basically the opposite. You get better leaving groups as you go from left to right, and as you go from top to bottom. Right? So, for example, if we were comparing the leaving group abilities of, let's say, OH minus versus Cl minus. All right. Now, what we're looking at here is specifically the atom that has the charge, right? So in this case, the oxygen has the negative charge in the OH, and Cl, of course, has the charge in Cl. All right. Well, if you look at the periodic trend here, oxygen is further to the left on the periodic chart than Cl is, right? So OH minus is considerably more basic than Cl minus. And you guys probably remember this. You know OH minus is one of the strong bases. So if we're talking about leaving group ability, Cl minus is the better leaving group. Excuse me. Okay? You can look at within a column as well. You could look at what's a better leaving group, F minus or Br minus, right? Well, you know from your periodic trend that F minus is a stronger base than Br minus, so since Br minus is weaker, that means it's a better leaving group. This can affect the reaction dramatically, right? The better the leaving group, the faster the reaction tends to go. And in some cases, if you have a really, really crappy leaving group, a terrible leaving group, the reaction won't proceed at all, right? For example, most of the time, if you're trying to rely on OH minus as your leaving group, that's not going to work, right? It just won't react. It just won't, react at all as far as a substitution. Okay, so being able to identify what are good leaving groups and not so good leaving groups is going to be important. I'm going to make mention of some tables that are present in Chapter 7. Now, I don't have pages for you because our editions are probably different, but I want to highlight there is a table in your book that has a list of common good leaving groups and common poor leaving groups. I don't necessarily want you to memorize it, but it certainly wouldn't hurt to become a bit familiar with it and be able to recognize, sort of off the bat what's good and what's bad as far as leaving group ability. Okay? All right. Let's take a look at the nucleophile. Now, we have basically two classifications of nucleophiles. They can be strong nucleophiles or weak. Strong nucleophiles tend to react in one type of mechanism. Weak nucleophiles tend to react via another mechanism. So it's going to be important to recognize which one's which. All right. In general, there's a couple of rules, a couple of guidelines that you can remember. In general, the stronger the base, the stronger the leaving group. Excuse me, not leaving group, gosh. The stronger the nucleophile. That would make no sense. Yeah. And so this directly follows the periodic trend for basicity, right? So if it follows that basicity trend, shows to be a stronger base, then chances are it's going to be a pretty strong nucleophile as well. Okay? I also mentioned that we could also have negative nucleophiles or neutral nucleophiles. Excuse me. All right. In general, negative nucleophiles tend to be stronger, although there are a couple of exceptions. Generally, we can say negative nucleophiles are stronger than their neutral conjugate bases. All right. For example, NH2 minus. NH2 minus is it's called the amide ion. It is an extremely strong nucleophile because it's also an extremely strong base, right? The conjugate base of NH2 minus is NH3, which is ammonia, all right? And that's neutral. And ammonia actually is a nucleophile. It can definitely be worked into nucleophilic substitutions, but it's a weak nucleophile. It's a weak base. It generally follows that trend, right? So, same thing you can see. My wife's calling again. I really hope I don't get in trouble. Keep me in your thoughts. All right. OH minus versus water, right? You guys know water isn't strongly basic. and therefore it's not a very strong nucleophile. It's classified as a weak nucleophile. Whereas OH minus, since it's a strong base, also a strong nucleophile. All right. Now, there is one exception. And when I say one exception, I don't mean just one compound or one species, but one situation. All right, I am going to give an example of this, though. Let's take a look at this guy. This is known as tert butoxide. All right. Like most, items with a negative O, this is a very strong base. Really, really strong base. All right. However, this is classified as a non-nucleophile. It's not even strong enough of a nucleophile to be weak. It's just not a nucleophile at all. All right. So this one sort of bucks the trend that we saw before, right? Why is this the case? Well, remember, and I don't actually remember if I told you this or not, but I'll tell you now. Whenever you don't know the answer in organic chemistry, half the time you can say steric hindrance and be correct. Not literally, but it just seems like that. That's why this is not a good nucleophile, because of steric hindrance. Simply put, crowding. All right? The negative oxygen here has a really big, bulky group. Tert butyl groups take up a lot of space, right? So simply speaking, it can't get close enough to your partially positive carbon in your alkyl halide to cause the leaving group to leave. It's just too crowded, right? It can sort of edge on the peripheries and steal a proton, right? That's where it can act as a base, but it doesn't have to get as close to do that. To actually bond to the carbon, it's really got to worm its way closer to the inside of the molecule. All right. So the one exception we see here are strong sterically hindered bases. They tend to act as non-nucleophiles. All right. All right, and the last thing I want to go over, and this is the last thing in this video, are solvent effects. All right, there's going to be basically two types of solvents that we use in nucleophilic substitutions. They're both polar. All right. First type is polar protic solvents. Polar protic solvents are solvents that can hydrogen bond. So, for example, water, of course, is a polar protic solvent. Ethanol, polar protic solvent, right? Several other types of alcohols, etc. And the second type is a polar aprotic solvent. These have dipole-dipole interactions, but no hydrogen bonding. All right, so for example, we have several that we can look at. Acetone, right, is an example. We can have one that's very similar to acetone, except instead of a carbonyl carbon, we have a sulfur there. This is called dimethyl sulfoxide, but more commonly we refer to it as DMSO. You can have this guy, this little ring structure with an oxygen in it. That's called tetrahydrofuran, which we call THF for short. Again, I'm going to refer to a couple of figures in your book that list commonly used protic solvents and commonly used aprotic. So again, it would probably be a good idea for you guys to sort of take a look at those and get familiar with some of the more common ones. I do have my pet solvents that I tend to use more than others, but I want to try to use a bit of a distribution so you can get used to seeing several different ones. All right. All All right, so polar protic and polar aprotic. And I mentioned that these can affect, rates of reaction. They can also affect nucleophilic power. And here's something that's kind of interesting. Let's just look at the halogens, right? Let's look at the halides. Actually, F minus, Cl minus, Br minus, and I minus. Okay? Now, we learned a periodic trend. We learned that you increase in basicity as you go from bottom to top, right? And how does that correspond with nucleophilic power? Well, the stronger the base, the stronger the nucleophile. So what we learned previously is that as you go up the column, the basicity increases, and we actually call it nucleophilicity. Sounds very cool and elegant when you say it. Unfortunately, it takes up a lot of space, so I'm just going to write NUC for short. The nucleophilic power increases as you go from bottom to top, right? And generally, in a vacuum, that's true if you're just talking in and of themselves. However, you have to take into context the entire components, every component of the system, right? It turns out this is true in polar aprotic solvents. This follows the expected trend. However, it's actually the opposite in polar protic solvents. So yeah, there's another factor here besides just raw basicity, right? These are called solvent effects. So let's take a look and see if we can figure out why this weird trend is going on. All right. First of all is really understanding how a solvent works. All right. Typically, like say you're trying to put in a halogen. Let's say, we're adding fluoride, F minus. All right. You don't just have a jar of F minus sitting on the shelf, right? They come as salts, right? It would be sodium fluoride would be a common example. Just like the sodium chloride, you get table salt. All right, so what you have to do is you have to take a salt, and what it does is it dissolves in a solvent and dissociates into ions. Okay? It's nothing new. You guys have talked about this before in Gen Chem. How does it actually do it, though? How does a solvent actually get the ions to break apart? Well, here's how. Right? And I'm about to show you what happens in a protic solvent. All right, so sodium ion has a plus charge, right? Well, think about it. In order to dissolve, and the ions have to interact with the solvent. Let's take a typical solvent here. Let's just say we have a polar protic solvent. Let's say we have water. All right, what part of the water do you think is going to want to interact with a positive ion? You're going to want something that's negative or partially negative. Well, guess what? That oxygen's sitting there, and we know that oxygen's got a pretty strong partial negative charge. And so what happens is several waters can interact with the sodium with their partially negative charges. There's not a set number. I'm just going to draw 4 because, well, that's about all I can fit on here. But they sort of surround it like this. Okay? This forms something called a solvent cage. You can almost think of it sort of like a little prison cell of solvent. All right? That'll be important. All right? So that's how the sodium gets solvated. Kind of funny. We actually don't really care about sodium because sodium is what we call a spectator ion. It's not actually involved in the reaction. What we really care about most is what happens to that fluoride. All right? Well, fluoride's got a negative charge, but it can also interact with water. What part of water do you think fluoride interacts with? I'm sure you're saying the hydrogen because it's partially positive, and I'm going to say you betcha because you're right. Yeah. Fluoride can interact with the partial positives from hydrogen. just like that. Okay, and again, you see water can form this solvent cage around fluoride. Now, here's something that's very, very important to remember and to understand if you want to understand this whole, solvent effect on nucleophilic power. If you look at the solvent cage here, look at the interactions. You have a strongly partial positive H interacting with a strong negative on a fluorine, right? You have an H interacting with a very, very electronegative atom, right? These interactions that form between protic solvents and halides, these are hydrogen bonds. So you have hydrogen bond here, one here, one here, one here, right? Bunch of hydrogen bonds. That's going to be important. Keep that in mind. Okay? Now we're going to take a look at the same situation, but with... Actually, I'm rewind there. I'm not going to... I'm losing control of my words. All right. I actually changed my mind. I'm going to show you something else instead first before I get to the other point. Okay. Let's compare a couple of halides. All right. I already drew fluorine, and for some reason I erased it because I'm dumb, but I'm going to draw it again. So bear with me. So again, I'm just going to draw this fluoride trapped in its water solvent cage. Okay. All right. Now, another periodic trend we can recognize within a column is size. All right. As you go from top to bottom down a column, do you get bigger or smaller? Hopefully you guys recognize by now you get bigger. All right. So we're going to compare fluoride to iodide. All right. Now iodide is much less basic than fluorine. On its own, it would have less nucleophilic power, but it's very, very large. So I'm going to draw this more to scale. I'm going to draw a big old iodine, or I guess I should say iodide, right? And I'm going to show it interacting with the same number of same number of water molecules in our model here. Since I've been doing 4 with fluoride, I'll show 4 with iodide. Okay. Which one of these, fluoride or iodide, looks more trapped by its solvent cage? Right? Remember, these are H bonds. These are hydrogen bonds. They're very, very tight, very powerful. Do you think one of these would have an easier time escaping those strong interactions? I think it's going to be the one where the interactions are spread out. And so I think this guy is going to have a better time escaping your polar protic hydrogen bonds than your fluoride is, because it's so tiny. Okay? That's why iodide is a better nucleophile than fluoride in protic solvents. It may not be as strongly basic, but because of its size, it can escape the solvent cage easier and get to the carbon it's attacking, right? If the halide can't escape the solvent cage, it can never get to the carbon to bond in the first place. Okay? It's too bad we don't have live classes, because I used to do a really fun interactive demo with this, where I literally had people form solvent cages around other people and they tried to escape. It was a ton of fun. Can't do that, COVID-19, but Maybe someday, if you want to teach this to somebody else, you can remember that for your own demonstration. For all you budding organic chemistry professors out there. All right, now I want to show you what happens in an aprotic solvent. And just, I'm going to use a common aprotic solvent for this. I'll use acetone. All right, so let me show you what happens to fluoride. All right, what do you think we're going to have? What part of acetone do you think fluoride is going to interact with? Hopefully you guys recognize we have a partially positive carbon in there. Right, because the carbon shares a double bond with oxygen, so we definitely have a good dipole. If you hear something weird in the background, my corgi is barking outside my window, so please ignore him. All right, so you have that, and you would have the same thing happening. Oops, that's a terrible looking line. With iodide as well, right? So I'll just draw that. So the situation here kind of looks really similar to the last one I drew, right? You have this big old eye, kind of more spread out here. Amongst the acetone cage, whereas the fluorine is a little bit more, is a little bit smaller, so it's a little bit more surrounded. However, there's a key difference here. Look at the interactions between your halides and your carbons. Is that a hydrogen bond? No. That is a dipole-dipole interaction. And the key difference here is that the dipole-dipole interaction is definitely weaker than the hydrogen bond. It's weak enough that it doesn't matter how big your halide is, fluoride, iodide, whatever, they can each escape the solvent cage pretty easily in this case because those dipole-dipole interactions are a lot easier to break. So, since they can both escape their respective solvent cages, nucleophilic power depends only on basicity, and F- is a stronger base than I-, so in an aprotic solvent, fluoride is a stronger nucleophile than iodide. So, there you go. There is an example of the importance of solvents. Okay, I'm going to stop this video here, let you guys sort of watch this and digest it a bit, and then next time we will talk about mechanisms and what the requirements are for each of those. Be sure to look at those tables and figures I mentioned, the tables of good and poor leaving groups, the commonly used protic and aprotic solvents. I think I forgot to mention there's also a table in their chapter that has some commonly used nucleophiles, both strong and weak. All right, so go ahead, get beefed up on that, and then we will continue next time. Till then, have a good weekend.